Hello and welcome to this new lecture on mechanics applied to aerospace engineering. This week will be dedicated to the dynamics of rigid bodies. This will be an important lecture. After a quick introduction, we will take a look at the equations of the dynamics of a system of particles, from where it is possible to derive the equations for the evolution of a number of global quantities. Thinking of a rigid body as a collection of point particles that are linked together by the rigid body constraint, we will then apply these equations to a rigid body. After that, we will focus our attention on the discussion of systems of forces and torques, and we will derive an important theorem about the equivalence and reduction of this system of forces. Next, we will move on to the rotational dynamics, and in this context, we will derive Euler's equations. To close this lecture, we will take a look at the energy equation for rigid bodies and the equilibrium conditions for rigid bodies. Okay, so let us begin by considering a system of n free particles. This means that we have 3n degrees of freedom in our system, which requires 3n scalar equations to have a closed problem. These equations have to come from the dynamics equation of each individual point particle, where I goes from I to n, all right? Imagine in particular that we have 5 of these particles, as you can see here. So this is our system of analysis, okay? Here in this example, P1 and P2 are interacting with a repulsive force, as you can see here and here. These are action and reaction, so they are equal and opposite. Similarly, P1 and P3 have this attractive force, and on top of that, P2 is subjected to an external force, right? As you can see, I have divided this expression. I have separated the external forces from the internal forces. And in the following, we will use the capital F for external forces and the lowercase f for internal forces. Okay, the important distinction between these two is that the action and reaction of internal forces happens inside our system. Okay, so we have the two forces inside of our system of analysis, and external forces, only one of these pair of forces appears in our system, the other one is somewhere else in the universe. Okay, so this is the situation for a system of n particles. In the case of a rigid body, we can think of it as a collection of an infinite number of such particles, each of them with a differential mass. Okay. This in principle would suggest that we need an infinite number of equations multiplied by 3, but this is not the case because, as we know, the rigid body has a kinematic constraint that is very strong, and the number of degrees of freedom that a rigid body has is only 6. Okay, so 3 for the position of one reference point and 3 for the attitude of the rigid body. And this means that we only need 6 independent scalar equations. Returning to a system of n free particles, there is not much that we can do with equations. We really need all of them to solve the problem. However, there are some things that we can do to obtain the evolution of some global quantities. Okay, so imagine that we sum all the equations together. One thing that is going to happen is that all the internal forces are going to vanish. Okay, they are going to cancel out, and the reason is that the action and reaction pairs appear, all of them, inside of our system. So for example, in these 3 equations that I have kept in the slide, you can see that this force and this force are equal and opposite. Okay, so when we add them together, they will cancel out. Same happens with this one and this one, and finally also with this one and this one. And same will happen with all the others in the system. If we introduce the sum of all the external forces as the resultant external force, okay, and we just call it F, capital F, then we will be able to write the right-hand side of the sum of all these equations in a very compact way. Regarding the left-hand side, remember our definition of the center of mass. All right, this is just the first moment of the mass distribution of this system of particles. If we take derivatives twice, we see that what we have on the left-hand side here is the velocity of the center of mass and the acceleration of the center of mass. Okay, the center of mass is a point which will be somewhere in the middle of our swarm of particles. So you can probably see that what will appear in the left-hand side is the sum that you have over here. Okay, so we can rewrite all that as just the mass of the system times the acceleration of the center of mass. Okay, this is the equation of the evolution of the total linear momentum of our system of particles. All right. And the interest of this equation is that it allows us to see that the evolution of the center of mass does not depend on the detail of the evolution of each of the particles. It does not depend in particular on any of the internal forces. It just responds to the sum of all the external forces, and in that sense it is equivalent to the motion of a single point particle with the total mass of the system located at the center of mass and subjected to this resultant force F. Another interesting thing that we can do with all these equations is to cross them with the vector API, where A is any point that we choose as a reference and pi is the position of each of the individual particles. So you see these equations here, and what we can do is to sum them again, and just like before, something interesting is going to happen. All the torques associated to internal forces are going to cancel out. For example, we have this one and this one, which are equal and opposite again. Okay, you can see that if you take, for example, just two particles. Okay, so imagine that I have particle, this is point A, this is P1 and this is P2. Okay, so imagine that P1 and P2 are repelling each other. All right, the magnitude of these two forces are identical, they just happen to be on the same application line, but with different directions. Okay, if you take the torque, the moment of those vectors with respect to A, okay, since the distance between A and the line of application is the same for the two forces, the torques are equal and opposite. Okay, so they vanish. And the same happens with all other pairs of torques that you have here, this one with this one and this one with this one. Okay, so the only thing that remains on the right hand side are the torques associated to the external forces. If we gather them together and we give them a name, we call them the resultant external torque about point A, we just call it MA, then the right hand side becomes very simple. Regarding the left hand side, observe that we can rewrite each of these terms that we have here, okay, as this derivative. Okay, however, if you expand this derivative, then another term appears, so you have to subtract it, and that term is this one that you see on the right. Okay, of course, on this new term we have the velocity of pi with the velocity of pi. So since this is a cross product, this is not going to contribute to this result. Okay, this is exactly the same as we did in the lecture of point particles. We also apply this transformation to write down the equation of the angular momentum. Finally, if we sum together all these terms, by definition, what we have is the sum of these terms is the derivative of the angular momentum, the total angular momentum of the system. Okay, and then, well, when we sum the other term that we have over here, what we have is minus with minus that becomes a plus. So we have the velocity of A, and then we have the mass and the velocity of each particle, which when we sum together, we have the mass, the total mass, and the velocity of the center of mass of the system. Okay, so what we have here is the equation for the evolution of the angular momentum of the system of particles, the total angular momentum of the system of particles. Of course, we will usually pick the point A, the reference point A, from which we compute all the moments in a smart way, so that this term over here can be equal to 0. We will either take a point that is not moving, so the velocity of A is equal to 0, or we will take A equal to G, so that this cross product is equal to 0. Finally, there is one more thing that we can do with our family of equations, which is to dot them with the velocity of each point particle. Okay, so this is what we have done here to the equations as you see them. Now, the important thing is that what you have on the right-hand side, which is the power associated to the external forces and to the internal forces, in this case, the contribution of the internal forces does not cancel out in general. All right, we can have internal forces that exert net non-zero work on the system of particles. All right. There is, however, one particular exception which is very relevant for us for the rest of the lecture, which is that when the distance between two particles, say Pi and Pj, remains constant, then the contribution to the work or to the power by these internal forces does cancel out. Okay, so here you have the force on Pi between the interaction of Pi and Pj, and this is the power that is exerted on Pi. On the right hand side you have the power exerted on Pj, and we have that if the distance remains constant, the velocities must satisfy the condition such that this equation holds true. Okay, and then the contributions of the internal forces cancel out. Regarding the left-hand sides, for each of them, we can replace the acceleration with the derivative of the velocity, as you see here. And by introducing the dot product into the derivative, we can write that as the kinetic energy of each of the individual particles. So when we sum over, what we have is the equation of the kinetic energy, the total kinetic energy of our system. Here we have called W dot, capital W dot, the power exerted by the external forces, and lowercase w, the power associated to the internal forces. As we have seen, both external and internal forces may exert work in the case of a general system of particles, okay? And as always, each of them can be conservative or non-conservative. When all the forces, internal and external, that exert work on the system derive from a potential, in other words, when they are conservative, then it is possible to integrate this equation and obtain an equation of the conservation of the mechanical energy of the system, but only in that case. Actually, I want to tell you about the case of internal forces a little bit more in detail before we move on to the next point. Just like any other force, internal forces may be conservative, and that means that there must exist a function like this one, okay, an energy, potential energy function like this. You see that in general, this function depends on the position of Pi and Pj. Okay, here we are again considering just these two particles, Pi and Pj, as in the previous slide. So if this pair of forces is conservative, that means that this function exists and that the forces can be expressed in this way. Okay, you see that if we are using Cartesian coordinates, for example, we can write down the internal forces, the two of them in the pair, as the derivatives of this potential function with respect to each of the coordinates. Okay. This has this is generalizing what we know when we have the potential of a single point particle. Just to give you an example, imagine that we have these two particles, P1 and P2, which are joined together by a spring of stiffness K. Okay. In this case, the two forces, the force applied on P1 by the spring and the force applied on P2 by the spring, can be expressed in this way. Okay, you see that they are equal and opposite because they are action and reaction. We know that springs are conservative, so yes, in this case we can find a potential energy function, which is the one that you see here on the slide. Okay, you can check that if you take the partial derivatives as explained here with respect to each of the coordinates for the position of Pi and Pj, you will recover the forces as you have them over here. Okay, so this satisfies the definition of the potential function. Now, just a word of caution, because perhaps it's not so immediate. When you have this situation where you have a system of particles where there are internal forces that derive from a potential, okay, in other words, forces that are conservative, when you write down the equation of the conservation of mechanical energy, you need to add the potential of the pair of forces only once. Okay, it's not you have to add this potential twice, once for each particle. It's one time, once for the pair of particles, and that's it. Okay, so enough about general system of particles. Let us now dedicate our attention to rigid bodies. Okay, so as we said in the introduction, in the case of the rigid body, since we have the constraint on the kinematics of each of the points of the rigid body, given by the distance is between any two points is constant, which is also expressed in terms of the velocity field equation of the rigid body, we only have 6 degrees of freedom and we only need 6 independent scalar equations. All right, so we can choose from the equations of all the point particles that constitute the body and get 6 scalar equations, or we can use the global equations that we have found for a general system of particles. Those equations are the equations for the center of mass, okay, the equation for the translational motion of the center of mass, which tells us that its motion depends only on the resultant external force and nothing else. It does not depend on the specifics of the body, how the body is rotating, or the particular individual forces applied on each point of the rigid body. It just depends on the resultant force. The other one was the equation for the angular momentum of the rigid body. This is the rotational dynamics equation. We have to choose a point to write down this equation, a point A. Usually, as we said before, we usually choose A so that this term cancels out, and then we have something simpler. In fact, if we remember from our previous lecture, the definition of the angular momentum for a rigid body, here we have written it down in terms of the tensor of inertia about the point A, and then there was this additional term if the point of the rigid body that is on top of A is moving, then we can replace this into this expression and have an equation for the angular acceleration. Okay. Again, we always try to make our life as easy as possible, so we are going to try to choose A such that this term does not appear, and also such that this term does not appear. That requires that our point A has to be a stationary body point, okay, that doesn't have any velocity, no velocity of the body point, and no velocity of the point, the geometric point itself. All right. So when this is satisfied, the equation for the rotational dynamics is simplified, and you can write it as you can see over here. All right. Now, in this equation, we will see this equation in more detail later. You have to be careful because you have this tensor inside of the derivative, and the tensor of inertia is in general not constant in reference frame 0. So we have to take care about that. As we can see, when we have chosen the point A correctly, the equation of the rotational dynamics depends only on the resultant external torque about the point and the tensor of inertia about that point. Finally, we also have the equation of the kinetic energy. Now, since we already have here between these 2 points 6 scalar equations, the equation of the kinetic energy is not an independent equation for the rigid body. Okay, this is an equation that can always be expressed as a linear combination of the other 6. However, in some situations, it is useful to replace some of the 6 equation over here with the one that you have over here. Now, importantly, since in the case of the rigid body, the distance between any 2 points of the rigid body remains constant over time, the internal forces, although the internal forces are not 0, they do not exert any work on the rigid body. So the equation for the kinetic energy is simplified into this expression. All right, so next we are going to discuss systems of forces and torques applied on rigid bodies. Okay, it's important to note that what we are going to see from this point onward will only be applicable to rigid bodies, so not to general system of particles. So imagine that we have a rigid body, okay, over here, which is subjected to a number of forces. Okay, so imagine that here we have point P of the rigid body, here we have point Q, and this force appears on point P, and this other force appears on point Q, for example. There may be many more. All right, and this is the general situation that we will have in actual problems. We have to solve the motion of a rigid body that is subject to some individual forces, and we have to see how we can deal with this. All right. Now we say in this case that the body is under a system of external forces, and we can use this nomenclature if you want. All right. Now, as we have just seen in the previous slide, the dynamics of the rigid body do not depend on the individual forces. They only depend on the resultant force, defined as the sum of all these forces, and the resultant torque, defined as the sum of all the torques of all these forces about one point. All right. We can select the point that we want. It doesn't matter. It will not change the dynamics. Of course, it will just change our equations, but the result will be the same. So how can we reflect this fact? The fact that the dynamics of the rigid body do not depend on the details of each of the individual forces. It only depends on F and MA. Well, we say that this system of forces is equivalent to this other system of forces, right? Where we just have the force F and the torque MA applied about point A. All right. In general, we are going to talk about systems of force torques, all right, because we will combine them with the semicolon into these curly brackets. All right. Now, so whenever we have a system of forces, one of the first things that we are going to do is to decide on a point A that is a good one for our analysis, okay, to simplify our equations of motion. And then we are going to compute the resultant force and the torque of all the forces about that point. And then we will have the reduced system, the reduced equivalent system to our system of forces, and we will proceed to write down the equations of motion. Observe that the resultant force doesn't care about the point A that we choose to compute the torques, all right? Only the torque depends on the point A, of course. Whenever we have two systems of forces, we say that they are equivalent if they reduce to the same system of force torque, like you see over here, all right, about the same point, about one point, any one point. If you take two systems of forces, you reduce them to one point like this, and you get the same result, then they are equivalent. In fact, in some situations, it will be useful to be able to translate our reduced system, FMA, to a different point, for example, point B. Okay, so this may happen, for example, if we discover that point B is more interesting to simplify the equations of motion. So how can we do that? Now, imagine that we have our body, okay, and imagine that this is point A, and we have computed the torque. Let's draw it like this about that point A, that's MA, and the resultant force, F, okay, and we want to move this reduction to a different point, for example, point B. Now, as we know, the resultant force does not depend on the point that we choose to do the reduction. Okay, so clearly F remains the same. That means that we can draw it as the same vector as before. We'll just put it over here, but it's irrelevant where we draw it. Regarding the moment about B, that's the thing that changes. We can compute that as the sum of the moment that we had about A plus the torque that the resultant force applied on A creates about B. Okay. In other words, we consider this force and we take the torque from here. This is the vector that goes from B to A. All right, and that gives us the new moment MB. All right. If you want, you can rewrite this equation in a slightly different way, like that. Okay. And perhaps this is interesting because it shows that there are some analogies between this equation and another familiar equation that we know of, which is the velocity field equation of the rigid body. Remember that that equation can be expressed like this. So if you have a point Q, you have that the velocity at that point is equal to the velocity at the point P plus a rotational term, which can be expressed like this. Okay, so you see that the analogy between the mathematical analogy between these two equations appears if you compare the moments with velocities, okay, and the rotational term you compare it with this force term, okay, where omega plays the same role as the force and the distance vector is still the distance vector, okay. Another important aspect of systems of forces is the power that they do on our rigid body. So imagine again that you have a system of forces like that. Okay, so this is our body, this is Fp, and this is Fq, this is Q, and this is P. The total power that this system of forces exerts on our rigid body is equal to the sum of the individual contributions. Here you see that the relevant velocity that we have to use to compute the power of each contribution is the velocity of the point of application of each of the forces. Okay. Now we can rewrite this expression using the velocity field of the rigid body to replace each of the velocities that we have over here in terms of the velocity of a single point, a single reference point, for example, A, plus this other term. Okay. If we do that, we see that we have two families of contributions. On the one hand, we have all the forces multiplied by VA, and on the other hand, we have these other terms. About this second family of terms, observe that they are basically mixed products. In other words, they are a combination of a dot product with a cross product, and there is a property that tells us that we can rewrite them in this way. Okay, we can reorder the factors without affecting the result in this way. So finally, we can see that the first family of terms is essentially the sum of all the forces multiplied by VA. That gives us the resultant force multiplied by VA. This looks like the power that the resultant force is doing as if it were applied on the point A. The second family of terms, once you do this replacement here, will become the sum of the angular velocity omega multiplied by each of the torques of the forces about point A. So we can write it like this. And this is the power that the torque MA creates on the body. Of course, if you consider the reduced system of forces as reduced on point A, that's basically what you have. Okay, you have that the power is the sum of the powers of the force applied on A plus the torque about A. All right. Whenever you have a system of forces that is equivalent to another one, the total power that they will do on your body will be the same. Okay, depending on where you decide to reduce your system, in other words, depending on the point A that you select, you will see some of the power appearing here and some of the power appearing here. Okay, and this balance may change if you select a different point, because the moment of A will change if you change the point A, as we have seen. All right. However, the total power created by the system has to remain the same if the system is equivalent to the original one. Now, finally, we can generalize everything that we have said so far about system of forces if we allowed also for the possibility of having external torques. Okay, so how does one of these external torques look like? Essentially, it's a torque that is not applied on any particular point. It's just an interaction that exists between the rest of the environment and our rigid body. But if it helps, you can visualize this for example, as a pair of forces of equal magnitude and opposite directions that are not applied on the same line of action. Okay, so this pair of forces, you can replace them with torque, as you can see, all right, without changing at all the effect on the rigid body. So in some scenarios, it might be more useful to represent or describe the interaction of the environment with our rigid body in terms of external torques like this, rather than forces, all right? And in general, we may have external forces and external torques like that. So what does change when we have these external torques? Basically, nothing in what regards the total force. Okay, the resultant force is just the sum of the forces that we have in our system. The only difference is that in the total torque, in the resultant torque, we have to add these additional contributions. Just that. Everything else that we have seen so far remains the same. Okay. For example, the power associated to the system is just as before. The power associated to each force with the velocity of its application point, and then we have these additional power terms which arise from the torques, all right? And this still reduces to the formula that we have seen before when you reduce the system. Next, we are going to discuss the rotational dynamics of the rigid body in more detail. So as you have seen, the translational dynamics equation doesn't pose any new challenge. It's basically identical to the equation of a point particle located at G. However, the rotational equation is something new, so we should discuss it in more detail. Now, in the following, we are going to assume already that we have selected the point A about which we compute angular momentum and the moments of the forces, etc., has been selected in a way that removes the extra terms on the right-hand side and in the definition of the angular momentum. And for that, there are basically two options that we can follow. Either we select a stationary body point, if there is any, okay, this will be option 1, or we choose the center of mass G as our point A. That would be option 2. Usually when there is a fixed point of the rigid body, for example, when we have a body that has been pinned to the origin at some point, usually in that case, the first option is preferable. In any other circumstances where the body is free to move in space completely, the second option is the way to go. When we have applied this, the equation for the rotational dynamics looks particularly simple. However, don't let this equation deceive you because it is quite complex. You see, you have the tensor of inertia here inside the derivative, and you are taking derivatives in reference frame 0. And this tensor is not constant in reference frame 0 unless the body is not rotating with respect to reference frame 0, okay, and it's not moving. So in general, this will not be the case. So you can either take the derivatives of the tensor, okay, or you can apply the Coriolis theorem to bring this derivative into reference frame SB, a body fixed reference frame where the tensor of inertia will be constant, okay. In that case, you can take the tensor of inertia outside of the derivative. You see that the derivative now is in reference frame B, and as a result of applying the Coriolis theorem, this new term appears. In general, this new term is non-zero because omega is not the same vector as the angular momentum vector. It only cancels out if the tensor of inertia has the same eigenvalue 3 times. Basically, that would be the tensor of inertia of a spherical body, for example. In any other case, this term will not vanish. So we can move it to the right-hand side, and the equation can be expressed like this. Remember that the derivative of the angular velocity in reference frame 0 or in reference frame B is the angular acceleration, okay? And this is the final result. This equation is what we usually call Euler's equation, expressed in this way, okay? When you express it in the body fixed reference frame, applying the Coriolis theorem. So one thing that we can do to gain some understanding of how this extra term is affecting the rotational dynamics is to project this vector equation in a principal basis of inertia. Right? So imagine that we have already diagonalized the tensor of inertia. We have found three eigenvectors, E1, E2, and E3, and the associated eigenvalues are I1, I2, and I3. In that case, if you project this equation along E1, E2, and E3, you will get these three scalar equations. Okay, and here is where you can see the influence of these extra terms. So, for example, if the body is rotating about one principal axis of inertia, for example, when omega 1 is equal to omega and omega 2 and omega 3 are equal to 0, right? If we focus on the first equation, you see that this term cancels out, okay? Because we have a 0, then this also is equal to 0, and this is equal to 0. So all these terms do not appear. This is what we call a clean rotation about one of the principal axes of inertia. If there are no external torques as well, okay, imagine for now that we don't have any of these, then the body would basically remain rotating about the principal axis of inertia in a very simple way. However, when this is not the case, when at least two of the components of the angular velocity vector in the body axis are not zero, okay, then we have a coupling between the different equations, and the coupling appears in these terms, as you can see. All right, and this means that the body will not rotate cleanly about one of the about the single axis of the body. The angular velocity vector will evolve over time, and it will evolve even if there are no external torques, just because of these coupling terms. All right. I don't think there is a clear name for this, but we can call this a dirty rotation if you want to compare it with a clean rotation from before. So this is a very rich behavior. We are going to spend a lecture dedicated basically to understanding this. We will analyze what happens when indeed you don't have any external torques. That is basically the problem that is called, quite appropriately, the torque-free motion of the rigid body. And we will see that when the tensor eigenvalues, okay, the principal moments of inertia, are all distinct, you have a very complicated behavior of the rotation of the body, even in the absence of any external torques. All right. Here you can see also another condition where the rotation can simplify. If some of these principal moments of inertia are equal, these differences will cancel out. So in that case, there will be no coupling associated to the corresponding equation. All right, so you see that there is this interplay between the moments, the value of the moments of inertia, and the angular velocity components in the body fixed reference frame. Observe that the three components, okay, that we have used here for this discussion are the components of omega in the body fixed reference frame given by this basis. All right. As an example, what you see here is a clean rotation where the angular velocity vector and the angular momentum vector are aligned parallel to each other along one of the principal axes of inertia of this boxed rigid body. So basically, as you can see, the rotation is quite simple. The body just rotates about that axis. However, observe what happens when there is just a tiny misalignment between the principal axis of inertia and the initial angular velocity vector. As you can see, the body now is tumbling, doing some weird rotation rather than the clean rotation that we saw in the previous example. Okay, this is just a result of the coupling between the different terms that appear on the right-hand side of the Euler equations due to the cross product of the Coriolis theorem. Okay, in these two examples, we have not included any torque, any external torque on the rigid body. Regarding the kinetic energy equation of the rigid body, let us consider that we have a system of external forces and external torques like this one, which we can of course reduce to a resultant force and a resultant torque about a point A like that. Now, when we try to evaluate the right-hand side of the equation, we have the power associated to these external forces and torques. We can do two things. On the one hand, we can work with this description of the system of forces and consider the contribution of each of the individual terms that you have over here. So you will have two families of terms. You will have the force terms, which will look like this, all right, where the velocity, the relevant velocity, is the velocity of the point of application of each individual force. And you will have the torque terms, which involve the angular velocity of the rigid body. Clearly, we can see what is the condition for each of these terms to be always equal to 0. On the one hand, the force terms, the power associated to the forces, are 0 when the forces are perpendicular to the velocities of the rigid body at that point, at the point of application. Okay, so when that happens, those forces do 0 work. For the torque terms, okay, for the external torque terms, the condition is that the torque has to be perpendicular to the angular velocity vector of the rigid body. And when that happens, the torque exerts 0 work on the rigid body. On another side of this discussion, we can see that a force or a torque is conservative. Okay, we say that they are conservative if the work done by it from some reference configuration of the rigid body to the actual configuration of the rigid body can be expressed as a function of the generalized coordinates only. Okay, we will call that function v or minus v if we want to include the sign criterion, the convention of the sign into the definition. So basically, we need to have something that looks like a function v of the generalized coordinates of our rigid body. Imagine that we are using the coordinates of our center of mass, okay, and the Euler angles. So in general, it will be a function of these 6 variables. Okay, so if we can express the work carried out by one force or one torque from when the body is in some configuration that we say a reference configuration to the current configuration of the body, if that can be done, if we can express that work in terms of only the generalized coordinates, then we say that the force or torque is conservative. Okay? And moreover, it will be possible to write down the force or torque in terms of the partial derivatives of that function with respect to the generalized coordinates. Okay, this function may be more or less complicated depending on the coordinates that you are working with, but the force or torque can always be expressed in terms of the partial derivatives with respect to the coordinates. So you see, this is the generalization of the definition of a conservative force that we had seen in the context of point particles to conservative forces or torques in the context of rigid bodies. The other alternative to write down the right-hand side of the kinetic energy equation is to work directly with the reduced system. So we have the resultant force and the resultant torque about A. Okay, so when we do that, what we have is, as we have seen in a previous slide, the power associated to the resultant force acting on point A and the power of the torque MA acting on the body. So we see the angular velocity of the body. And of course, the same comments apply to the ones that we have done before. So if the resultant force happens to be always orthogonal to this velocity, that term will be equal to 0. And similarly, if this is orthogonal to this, then it's always equal to 0. All right. And again, we can also discuss whether the resultant force or the resultant torque are conservative or not in the same way as before. when all the forces and torques that exert a positive or negative work, in other words, a non-zero work on the rigid body are conservative, then the mechanical energy of the rigid body will be conserved. And this mechanical energy is defined as the sum of the kinetic energy of the rigid body plus the potential energy function associated to the conservative forces and torques. To conclude this lecture, let us review the concept of equilibrium in the context of rigid bodies. Basically, what we want is to define what are equilibrium configurations and what is the stability of an equilibrium configuration. Now, we say that a configuration, which remember is the sum of the position and the attitude of the rigid body, is an equilibrium configuration if when we leave the body at that configuration with zero velocity, zero translational velocity, and zero rotational velocity, the body will remain there forever. This requires, of course, that the acceleration of one point, any one point, for example, point P, be equal to zero, and that the angular acceleration of the rigid body be equal to zero. If this is true, then the acceleration of all points of the rigid body will be equal to zero. Of course, if we look at the equations of motion that we have defined in this video, the condition that the acceleration is equal to zero and the angular acceleration is equal to zero can be expressed as the condition on the resultant force and the resultant torque about a point, any one point, for example, a point A, be equal to zero. Okay, if the force and the resultant force and the resultant torque about one point are equal to zero, they are equal to zero about any other point. When we have an equilibrium configuration, it's very interesting to discuss if it is stable or not. All right. So the concept of stability is the same one that we have introduced before. Basically, the stability pertains whether if we perturb the configuration just a little bit by moving the rigid body or rotating it a little bit or applying some translational or rotational velocity to it, the rigid body will not go anywhere far from the equilibrium configuration. It will basically oscillate about it or return asymptotically to it. So when that happens, we say that the position and attitude, in other words, the configuration of equilibrium are stable. Okay. In any other situation, of course, we say that it is unstable. Mathematically, we can extend the mathematical definition of stability that we had introduced for point particles, as you can see over here. Essentially, if we take, for example, point C to express our velocity field and 313 Euler angles to express our attitude, we say that an equilibrium configuration defined by a given position of C and some values of the Euler angles is a stable one if for whatever values, for whatever positive values of these epsilons, you can always find values for these deltas, okay, positive values for these deltas, such that if your perturbations of the equilibrium configuration are smaller than the deltas, the subsequent motion of the rigid body will be such that these distances to the equilibrium configuration will remain smaller than the epsilons for all values of later times. Okay, so if this happens, then the condition is stable. In any other case, the condition is unstable. So that's it. Thank you and see you next time.